All right, this is a little video about specific heat. So let's talk about what this means. Specific heat is a pretty interesting concept. It's the amount of heat energy that exactly 1 gram of a substance must either absorb, as in an endothermic process, or release in an exothermic process, so that the temperature changes by 1 degree Celsius. So it's the amount of energy that you got to put into 1 gram of a substance to raise its temperature by 1 degree, or it's the amount of energy that's got to be lost by 1 gram of a substance so that its temperature drops by 1 degree. Okay, so picture this. For water, those amounts are this. So pure water has a couple of different specific heat values because we can measure them with different units. And these are equivalent to each other, actually. So the specific heat value for water in terms of joules per gram is 4.18. And we can also equate that to exactly 1 calorie per gram. Okay, so these are equivalent values. What that means is that if you had 1 gram of 30-degree water, so this little box represents 1 gram of water, and let's pretend it's at 30 degrees Celsius. If you wanted to make that into 31-degree water, you would have to apply 4.18 joules, or you could apply 1 calorie. They're the same amounts of energy. If this water was going to cool off to 29 degrees, it would have to release 4.18 joules, or it would have to release 1 gram. Okay, see how that works? Okay, so like everything we do, there's a math equation that goes along with this, and here it is. This is delta H, which we're familiar with now, equal cmΔT. Okay, and here's what those variables mean. The delta H, as you know, it's the amount of heat energy that's either absorbed in an endothermic process or released in an exothermic process. C is the specific heat value. The only one you know right now that I just told you was for water, but every substance has its own specific heat value. That's why we call it specific heat, because the value is specific to the substance. Okay, and then mass, that's the M, that's got to be measured in grams, and then our temperature change here, delta T, that's, remember we're working in degrees Celsius for these problems, okay? And so these are 4 variables in an equation, and like a bunch of other stuff we've done, as long as you have 3 out of the 4 variables, you can solve for the 4th, and here's what those other derived equations look like. So this one is the one that we just looked at. But if you wanted to isolate the other variables, you know, C is delta H over M times delta T. Mass could be solved for by dividing delta H over C times delta T. And delta T can be solved for by dividing delta H by C times M. All right? So let's go ahead and do a couple of practice problems here and get you good at this. Here's the first kind of problem. This one's pretty easy, I think. How many joules of energy are released as 50 grams of water cools off from 90 degrees to 20 degrees? So here we're looking at an exothermic process where energy is being released, and we want to know how much energy that is being released. And that depends on how many grams of water we are and how much temperature change is. Okay, so let's set up our equation here. Delta H is what we're solving for, the amount of energy released. And we're going to set that equal to C, which for water is 4.18. Okay, that's the specific heat value for water, because we're talking about water. And then we're going to multiply that by the mass of water, which was 50 grams. And the temperature change, so this is just the difference between the starting and ending temperatures, and this is 70 degrees, okay? So we just calculate this, times 50 times 70. Okay, so 14,630 joules of energy were released. Okay, So it's pretty easy. Now, if this question would have said how many calories of energy are released, so if it's a calorie problem instead of a joule problem, then you would use 1 instead of 4.18. And that just goes back to water's specific heat values. Remember, if it's joules, we use 4.18, and if it's calories, we use the 1, okay? Alrighty, let's do another one. All right, if 2,500 joules of energy are absorbed by 0.75 liters of 40-degree water, what will the temperature of the water be? Okay, so a couple of things here. Right off the bat, we're solving for a delta T here, but our mass of water is kind of in a weird setting here. It's in liters, but remember that for water, 1 milliliter is equivalent to 1 gram. Okay, that's just for water. But what that means is that we can basically consider the fact that knowing that there's 1,000 milliliters in a liter, this is actually 750 milliliters, which equates to 750 grams. Okay, so that's the mass that we're going to use in this problem. So we'll set it up to solve for delta T. And this is delta H over C times M, okay? So delta T equals our delta H, which is given to us as the amount of energy absorbed, right? So that's 2,500 joules over the specific heat of water times the mass of water. And because, again, we're working in joules here, we're going to use the 4.18. And we're going to multiply that by the mass of water that we have, which is 750. And let's figure out what that is. So that is 0.797, degrees. Okay, so 0.797 degrees is our temperature change. That means that that's not our final answer. We want to know what the temperature of the water is going to be when the original temperature changes by our delta T, right? So it's increasing in temperature, so we put all those joules of energy into that, and we only got less than a degree of temperature change, so our new temperature of the water is 40.797 degrees. Not a huge temperature change, but that's because a joule is not really a huge amount of energy, believe it or not. It's actually a really tiny amount of energy. So anyway, you can sort of see how these problems can be set up. Just keep these 4 variables in mind, these 4 equations in mind, depending on which variable you're solving for, okay?